between distributions. So far we've looked at the empirical rule and normal distributions. So what do we do when the data is skewed? Now remember, when we're talking about skewed data, well, let's talk about first off, here's normal. That's pretty much when you cut it right down the middle and fold it in half and be equal. And then we have skewed when the main area, the main data, is either to the left or to the right. So remember, most of my data is up here to the right, so this is actually skewed left. And remember, it's kind of opposite the way some people think, but if most of the data was good, but some of the grades were lower, that's pulling the average down. And if most of your data is down here, but there's some data up here, it's pulling the average up or to the right. So this one is skewed right. Just a quick reminder. Okay, so that's what we're going to talk about now. So down here we have a list of ages and genders of 50 people. Now we can't use z-scores unless we have a normal curve. To make data into a normal distribution, we use samples. The more samples, the more normal the curve. So as we get, think about it this way. If I flip a coin 5 times, I might get 4 heads and 1 tail, which is definitely not what we expected. We expected, well, technically 2.5 each, but let's say 6 times. 3 heads and 3 tails is what I expect, but I get 5 and 1, or 4 and 2. But if I do 100 flips, I should be much closer to 50-50. And if I did 1,000 flips, I would get closer to 50-50. So the larger the sample, the less chance of skewing we have. So we're going to use a gravity calculator to randomly select a sample size of 5. Okay? So I'm going to do it like this, right here, random sample, 1 to 50, because there's 50 people. I want to pick 5. Or you can do it one time and just click OK 5 times to make sure you get no repeats. We talked about that. So I'm going to say, I already did this. So I got this person right here, person number 1. I got person number 6. I got person number 12. Person number 28. And person number 47. That's what I got. All right? If you ran this, you'd get a different 5 numbers. If I ran again, I'd get a different 5 numbers. Now, it says calculate the mean of your sample and graph it below. Then repeat it with 15. Now, what we have here, this graph is, if you think about it, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so let's pretend that as a class, we all did 5 random people from this list. And then I gathered up 20 people from my class to tell me, what did you get for an average age? Okay? So this is, say, a class set. This right here is a class histogram of 20 students after everybody did a sample of 5. And then, if you look at this, here's 1, 2, 3, 4, 9, 11, 12, 14, 15, 16, 17, 18, 19, 20. So this is also 20 students. But notice 20 students who did a sample of 15. So if we all did 15 and reported our average, look at the difference in the 2 histograms. Okay, this one, if my board would cooperate, way spread out. But here, much closer to normal. Now this one's still a little bit skewed right. More of our data is to the left. But it comes closer to a normal distribution with a sample of 15 than a sample of 5. So, let's talk about all the data. If you take the original 50, you get an average of 41.2 with a standard deviation of 15.3. The class sample, with everybody doing 5, the class sample I gave you right there, was 42.6 with a standard deviation of 9.48. When we did 15, now you're going to not believe that this was true, but it actually matched with a much smaller standard deviation. So the mean actually ended up being exactly the same. Now that's a rare occurrence. Maybe you might get 41 or 41.5, but you can see what happened as we got more samples. So, in the HIT class histogram, for the 20 students scattered, how does the mean of the sample means compare with the population mean? Well, as the samples got larger, the sample mean got closer to the population mean. And in this case, it was actually exactly right on, which is a rare occurrence, as I said. What happens to standard deviation as the sample size increases? It gets smaller. It decreases. What happens to the shape of the histogram as it increases? It gets more symmetrical or normal. So the central limit theorem. Properties of sampling distribution of the sample mean. So we're working on a sample now. All right, sorry for that pause. The board was not being responsive. So we're talking about the sample mean. Okay, so we're talking about not the population, but the sample. So it says if a random sample of any size, whatever you're given, is selected from a population with its mean, remember this funky looking U is the symbol for mean, and a standard deviation, there's that symbol. Then, now this is kind of small writing, but this right here is the sample mean. Okay? So you know you have that funky U like mean, but then you have the X bar. So we're going to kind of summarize down here. So this funky U X bar is the sample mean. As opposed to just our funky U, which is the population mean. All right? We're also going to refer to the X over it as a sample standard deviation, which we talked about on our calculator. And then this is going to be different than the calculator. This is the population standard deviation. Now remember on the calculator, we refer to that as SX. Okay, but an actual mathematical symbol is just the O, the funky looking O. Okay, so back up here. Number one, the sample mean is equal to the population mean. And in here, the sample standard deviation is equal to our population standard deviation divided by the square root of our number. And last, the sampling distribution of the sample mean is normal if the population is normal. Okay? But for every other population, as we get more, as the sampling size increases, the mean is going to approach a normal distribution. Now, this is very important. We want to have at least 30 in our sample. Okay, that's our magic number. I'm going to refer to that many times. Our magic number is 30. We want to have at least 30 in our sample to get a good representation. And just a note, if we want to use z-scores, sample has to be greater than or equal to 30. So we're not going to use z-score if it's not greater than or equal to 30. All right. Talk about sample mean some more. If one looks at the number of ounces of soda in the U.S. adult drinks per day and their total, the graph of this data would show the population distribution. It would almost be impossible to graph all the data to look at the population, and the population might not be normal. So if we look at a sampling distribution from a size of 30 or greater, we can count on it being normal. So let's say X is the number of ounces of soda a U.S. adult drinks. The mean is 20, and standard deviation is 3.2. Okay? So again, our symbol is 20, and standard deviation is 3.2. What is the mean and the standard error of the sampling when n is 50? All right? So, we see this term standard error. Let's go back to the previous page. I did forget to mention something. Right here. So, the sample standard deviation of the sampling distribution is also known as the standard error of the mean. So, standard deviation of the sampling is also known as standard error. All right. So, what is the mean and standard error of the sampling distribution when n is 50? Well, we're going to say this is 20 also, because remember we said when normal these should be equal. And then we said the standard deviation is equal, the sample standard deviation is equal to the population standard deviation divided by the square root of the number. So that works out to be 0.4525. So we're calculating z-score. Remember, z-score is your actual score, so this is 20.5, minus our mean, and we've been using 20, divided by your standard deviation. But since we're looking for the sample z-score, we're going to use our sample standard deviation, 0.4525. And please remember when you type this in your calculator, hit enter after you hit 20 and then divide by 0.4525. Otherwise, your order of operations will divide 20 by 0.4 and then subtract that from the 20.5 and you'll get a wrong answer. So you should get 1.104, so it's going to be 1.10. That's our z-score. So just slightly above one standard deviation. What would the mean and standard error be of the sampling when n is 20? Well, again, we're going with our mean of 20. So our sample standard deviation, or our standard error, is equal to 3.2 divided by the square root of 20 this time. Now remember, 20 is below our magic number. So you have to be cautious about this. It ends up being 0.71. So the standard error, or the standard deviation of the sample is 0.71. But our magic is below our magic number. But remember, up here they did tell us that it's normal. Okay? If we're looking at sample size from a sample of 30, it's normal. But with 20, it's, under that magic number. Now, if in the problem they tell you, hey, this is a normal population, it's okay to have a sample size of 20 or 10 or 7. But just be cautious that if you're not told it's normal, this is not as strong of a number because we did not reach that magic number of 30. Okay, now, last new thing is sample proportion. So before we talk about sample mean, now we're talking about sample proportion. All right? So, if random sample size of n, whatever our number is, selected from a population with a proportion, okay, a proportion, when we think about proportion, we think about percent. Then, back to our chart here. So our funky U shape with a P, that's our proportion. And that's going to be either a fraction or a percent. Because every fraction can be written as changed to a percent. And then n is our sample size, obviously. So, how do we calculate our standard deviation from a proportion? It's very simple. We take the square root of the proportion times 1 minus the proportion divided by n. And lastly, if both np and n times 1 minus p are at least 10, these are our magic numbers here, it's normal. Alright? This will make more sense once we do some sample problems here. Okay, in a population where 78% of the adults have been pulled over for speeding, a sample distribution is theoretically created with a sample size of 50. So, n times p, n of 50 times p is equal to, type in our calculator, and we get 39. And then n times 1 minus p, which means 50 times 0.22. And if you think about it, 78 cents plus 22 cents equals $1. So 1 minus 78 cents leads you to 22 cents. That's 11. And doesn't it make sense that 39 plus 11 makes 50? Okay? Because you're doing 50 times the 78% and 50 times the 22%. Now, we also want to make sure that both these numbers are greater than 10, which they are, so we're good to go. Okay? So, NP is greater than 10, and n times 1 minus p is greater than 10. So because they're both greater than 10, we know that the sampling distribution will have a mean of 0.78 and a standard error of square root 0.78 times 0.22 divided by 50, so about well, when that happens, 0.058, or approximately 0.06 rounded, either way. And it will be approximately normal because both of them are bigger than 10. So another example. We're almost done. Mean length of songs. So the mean is 3.7. Standard deviation of 1.3. They chose 30 songs. That's our n. Alright? So the sample mean, is it a sample mean or a sample proportion? Well, it doesn't say a percent of the population or a fraction of the population, so it's a sample mean. Condition. N's got to be at least 30. Check. It's exactly 30. Find the mean of the sampling distribution of the sample mean. So that's 3.7. So find the mean. It tells you that right here. Find the standard error of the mean. Okay? Well, that's again is equal to our standard deviation divided by the square root of the number. And that works out to be about 0.24. Now, what interval captures 99.7%? Remember, that's from -3 to +3 on our normal distribution. That's a horrible drawing. So here's -3 and here's +3. 99.7 is that area right there. So, if we put, that's a better one, we put in the middle 3.7. So we found out that was our mean. And then we're going to add 0.24. So this is 3.94 and 4.18 and 4.42. And then minus 1 is going to be 3.46. Minus 2 is going to be 3.22. And minus 3 is going to be 2.98. Now again, we just start with our mean and we add the standard deviation, or actually the standard error in this case, each time and subtract it each time. So, minus 3 is here, plus 3 is here. So what interval? It's from 2.98 to 4.42. That's the interval that captures 99.7% of the population. And our last example, about 23 out of 100. 23 out of 100. That's a fraction, which is also 23%. They have a block. Raphael chooses a sample of n equals 85 as high school. Well, this is a proportion because it's 23 out of 100, or 23%. The conditions. Well, first off, 0.23 is our P. N is 85. So our conditions are N times P. So 85 times 0.23, which is 19.55, bigger than 10. We're good to go. Then we have to do N times 1 minus P. So 85 times $1 minus 23 cents is 77 cents. And that works out to be 65.45, which is definitely bigger than 10. So our conditions have been met. The mean is 0.23. That's the percentage changed to a decimal. The standard error, again, of P is equal to, this is our new formula, P, which is 0.23, times 1 minus P, 0.77, divided by N, which is 85. And that works out to be 0.045, or approximately 0.05 rounded to the 100 spot. And then what proportion, we're almost done, captures 68%. Well, remember, 68% is between +1 and -1. So if we start at 23, and we go up, 0.23, and if we go up 0.05, 23 cents plus 5 cents is 28 cents. And if we subtract, we get, I don't know why I started to put a negative. Let's see, about -1, I guess. Subtract, we get 0.18. That is my 68%. So from 0.18 to 0.28 is my interval that contains 68% of the population. And that's it.